So our next speaker is Sam Baldwin, also a physicist. He was a postdoc with Bob in the 1980s, when he was working on cleaner wood biomass burning, cleaner and more efficient biomass burning cook stoves, as well as more efficient electric motors. And he also, Sam and Bob worked closely together when Sam was organizing two energy panels that were convened by the President's Council of Advisors on Science and Technology, PCAST. Bob was on a couple of those panels, one in '97 and one in '99, and he worked closely with Sam, who was sort of overseeing those panels at the time, and they've continued a collaboration ever since. So Sam, take it away.
Okay, I want to especially thank Eric and his whole team for organizing this wonderful seminar. It's really a tremendous layout of people to celebrate Bob. And I want to also very especially thank Bob Williams. As Eric just said, I came here as a postdoc for 3 years in the mid-90s. Bob was a wonderful mentor, a colleague, and especially a friend for the last 30 plus years. So thank you, Bob. What I'm going to talk about very quickly are some of the energy challenges that we face, and they've already been touched on extensively. Then go into some detail on renewable energy technologies and where they're moving. And then finally, some grid integration issues and what the challenges are that are raised by that. Energy challenges, we know these very well. Energy security challenges, economic challenges in terms of costs, environmental challenges, and I want to focus in particular just on the greenhouse gases, because whatever you're hearing from Washington, I just want to simply affirm that climate change is real, it is serious, and we have to address it. So forget the other stuff you're hearing from Washington. So you've all seen this. Temperature increasing in the atmosphere with carbon in the black line. Ocean energy content increasing. And of course, related to this, as the carbon dioxide goes into the atmosphere, much of it is eventually absorbed in the oceans. And so you have ocean acidification. These are serious problems. They're going to have planetary impacts that we have to address, and we have to address as fast as we can. So how are we going to meet these energy challenges? Well, Howard has just described efficiency is critical. We want to do efficiency everywhere. It is the lowest cost resource. Fuels, Joan Ogden and others will be talking about those later today. And I'm going to focus on the electricity sector. Yeah, the possibility of fossil with carbon capture and storage, and Bob has been a leader in that area, nuclear power, and renewable energy. And so you can create an option space like you see on the right between renewables, nuclear, and fossil with CCS. And we're going to be someplace in that space. And I actually expect we're going to be and have an increasing share, a rapidly increasing share of renewables. So I'm going to focus on solar and wind. All of these face challenges: technical, economic, siting, variability of renewables, land use, environmental challenges. But much can be done with existing technologies, and we need to move them out as quickly as we can. But further R&D is needed to achieve the changes that are ultimately necessary. And so key questions are, how far can renewables go? How fast can we get them there? How well are they going to perform? At what cost? And what are the best pathways to get there? Solar. The US has great solar resources. So here's sunny Spain, and you can compare it to the United States, and you see that sunny Spain has nowhere near the solar resource that we have in the Western United States. Here's Germany on the right, and you can see that Germany, with all the photovoltaics that they've put in, well, their resource is similar to that of Alaska. So if you go back 7 years, this time in 2010, the goal and longstanding goal of the solar program at DOE was to move from, at that point, $3.40 for a utility scale PV system to get to $2.20 by 2016. And that had a module cost in the blue bar at the bottom center of about $1 a watt. So that was the goal. And the solar program said, oh, that's not good enough. We need to do much better than that. We need to get to $1 a watt, corresponding to about 6 cents a kilowatt hour. And that means getting to 50 cents a watt for the modules. So here we are 7 years later. How have we done? Well, module costs today are in the 40-cent range. And last week, I heard a report from the Bloomberg New Energy Finance that they were observing costs as low as 34 cents a watt for modules. And we're nearly there on the total system installed cost for utilities. We're just over $1 a watt. Job done? Well, here's what this has resulted in. So you can see the cost on the vertical axis by year on the horizontal axis. Costs have plummeted for utility scale systems. We're now below 5 cents a kilowatt hour installed, including the investment tax credit, of course, but below 5 cents in power purchase agreements. And this has been achieved by technology advances, economies of scale, reducing balance of system soft costs, and grid integration issues that we'll talk about. Here's the number that have gone into place by year on the horizontal axis. So this last year, over 7 gigawatts, 7,000 megawatts of PV systems were installed in the United States, bringing the cumulative total to over 14,000 megawatts, with the result that about 260,000 people in the United States now spend the majority of their time on solar, a huge job generator. And we can do more. A recent study on the path to sunshot estimates that we could have over 25% of US electricity by 2050 coming from PV, and that would be over 600 gigawatts of PV plus 80 gigawatts of concentrating solar thermal power. So, are we done with the job? No. Our solar program took a look at where we were. We've reached essentially the goals of Sunshot about 3 years ahead of schedule, which were considered crazy aggressive targets when they were first put in 2010. And now they want to cut the costs in half again, aiming towards 3 cents a kilowatt hour by 2030, roughly 50 cents an installed watt cost, with module costs at 25 cents. But it's important to note, well, we have many pathways to get there, lowering the module prices, lowering balance of system costs, improving lifetimes, and we can see a number of technology research pathways that could get us there. But that's not the total cost. We also have to worry about integration costs, and I'll come back to that in just a moment. Wind. The US has tremendous wind resources, and you can see in the purple down the middle of the United States where much of that wind resource is, and also along the coastal areas. How much is that? Well, the analysis indicates that it's the equivalent of over 10,000 gigawatts of installed capacity. And to put that in scale, the total United States electricity generating capacity today is about 1,000 gigawatts. So 10 times as measured by capacity, what we currently have. Here's a figure showing a similar map for Indiana, looking at wind speeds at 50 meters above the ground. And what this shows, going to 70 meters, and you see more and more of the purple color there, much better wind speeds just by going up a little bit higher. And here you see it at 100 meters. So there's huge pressure and a huge opportunity to reach higher hub heights. Now, if you think about Working on a wind turbine at 100 meters, you know you're up there. You know, I've climbed up and you really feel it up there. But huge opportunity. Tall towers, big rotors. Keep that in mind. So wind technology. It's now become a mainstream US wind resource with over 5% of US electricity last year and over 100,000 jobs across the United States. And here's what the power purchase agreements, including the production tax credit, look like, with last year costs in the neighborhood of 2 cents a kilowatt hour, and recently in the neighborhood of 2 to 6 cents, depending on where you are, what the wind resource is. And here's growth in the wind resource. So today, we are now over 80 gigawatts, 80,000 megawatts of installed wind turbines. And a recent study put out a year ago is that if we could successfully address all the challenges of facing the wind sector, it could supply over 35% of US electricity by 2050, requiring about 400 gigawatts, a little over 400 gigawatts of installed capacity. Job done? Again, not even close. There was a recent expert elicitation done by Ryan Weiser at Lawrence Berkeley National Laboratory for us, reviewed with 163 wind experts where wind could go. And the estimate was that about an additional, for the turbine itself, 25 to 30% cost reduction by 2030, 35 to 40% by 2050. How is it done? Well, larger rotors, taller towers, improved durability of components, especially for offshore systems where they're exposed to sea salt, improved foundation design, and so forth. So, substantial potential improvements in wind technology. But here's a picture from Hornsrev Wind Farm off the coast of Denmark. Weather conditions were just right, so you can actually see clouds forming in the wakes following the turbine. And you can see the tremendous amount of turbulence that's generated, and that turbulence lands right on the very next wind turbine. So what are the impacts? Well, estimates are that losses of up to 20% and higher are due to turbine wake interactions, turbulence, blade boundary, layer dynamics, and so forth. So a huge loss. Once you think about just working on the turbine, going to the whole wind farm and thinking about the synergies across the wind farm, there's, again, lots of potential to improve performance. In fact, some initial indicators are that just simply steering the wake of the wind turbine a little bit to miss the next turbine downstream might provide 14, 15% efficiency improvements. That's basically a software improvement that you could capture in existing wind farms. So now we've got a program going at the National Renewable Energy Laboratory in Colorado, where they are looking at modeling with very high fidelity using supercomputers the full details from the centimeter scale on the wind turbine blade up to the multi-kilometer distribution of those wind turbulence issues all the way across the wind farm to understand how to minimize these kinds of losses. Huge opportunity. But I keep talking about taller towers and big rotors. Here you see a bit of a problem with big turbine blades. This is an 80-meter blade. People are talking about even bigger blades. So what do we do? Well, that's a challenge. You don't really want to segment these because you introduce all kinds of failure modes, problems of how you reconnect all the pieces. Can you do manufacturing in the field and still have high precision, still get economies of scale and learning? It's a big question about how you actually do that. And there's some discussion about even looking at things like 3D printing of composites to do that in the field at the site. But this is a challenge. So now let's look at renewable electricity system integration. And you have here the whole range of different renewables that might go in. Geothermals, concentrating solar thermal, biopower, photovoltaics. And of course, those are going to be linked with the conventional systems, fossil and nuclear, to form an overall system. And you have to worry about the demand side. You have distributed generation with those rooftop PV systems. Demand response is an opportunity that's going into place. Distributed storage, smart grid issues that was already mentioned. Potentially controlled charging of your plug-in hybrid to match what's available on the grid. And the challenge is that resources are site-specific, they're variable and uncertain. So how do we integrate these? Now, going from the conventional historical system with centralized control, one-way power flow, the system is already changing dramatically, irrespective of renewables. And partly that's because we have so many electronic converters online, which have different response characteristics than the traditional grid has been used to. So we're having increased interconnection, decreasing rotational inertia. It's a technical issue involved with getting the inertia from the synchronous generators to support you. More control points. The whole system is becoming more stochastic. You've got variability on the supply side, you've got more variability on the demand side. It's less centralized. You have more multi-directional flows. It used to be the power would just go down the lines and right to the house, and that was the end of it. Now, if you have a lot of rooftop PV systems, the power is flowing all kinds of directions around that distribution grid. In summary, in some sense, we're going from a primarily analog system to a digital system in many aspects of the grid today. And that leads to all kinds of R&D opportunities. We're looking at issues like grid architectures, how we improve sensor and data acquisition. We'd like to be able to estimate what the state of the system is very rapidly, much more rapidly than we do today. And in fact, with modeling and simulation, optimization algorithms that we need to improve, we would like to have faster than real-time analysis so we can see if conditions are being set up on the grid that are going to lead to a fault so that we can intervene and solve that before there's a blackout. So lots of interesting R&D opportunities. One of the challenges is that we have to go, in this graph you can see across the bottom the time scale from milliseconds all the way to the right to decades. And those are the time scales you have to worry about when you're thinking about the grid. Everything from sub-second stability issues to hour-ahead scheduling of dispatchable resources, to day-ahead scheduling, to weeks, months, and decades for planning what the system is going to look like. So we need to do some modeling and thinking about how we do system integration. And a few years ago, I pushed through a big effort looking at what would happen with very large levels of renewables on the grid. So we started with the NREL REEDS Renewable Energy Deployment System model, which has very good spatial characterization of the United States. So 356 regions with hourly resource data in every one of those regions. But it's not got very good temporal resolution. Not bad when you take into account the statistics that it's able to do between periods. We then also used the ABB GridView commercial production software, and we were able to do analysis of the entire US grid down to the hourly level. That was covering 11,000 generators, 85,000 transmission lines, ultimately rolled into 136 transmission zones. And so along with REEDS and ABB's GridView, we modeled what the grid needed to do, what grid integration needed to do every hour of the year. Now, more recently, NREL is primarily using Plexos, which allows us 5-minute dispatch for looking at the systems. And to give you a sense of the level of detail, URGIS is the Eastern Regional Grid Integration Study. It had 5,600 generators that it looked at and 60,000 transmission nodes. It looked at every transmission line in the eastern United States at 69 kV and over. So an extremely detailed analysis. So here's the kind of results. When I started that study, it was the first detailed study looking at how high could renewables be pushed into the system. And so the axis here shows the capacity that was installed and then modeled with hourly simulation. You can see the gigawatts there, and we didn't know how far renewables could go in. Would the system work at higher levels of renewables? Would the costs go through the roof? And so we walked up in 10% increments. You can see 30% all the way up to 90%. And in fact, the system worked, and we did not see costs go through the roof. They did not have a sudden exponential rise. They just rose gradually, as you'll see in a minute. And we thought we'd try and break the system. We put all kinds of constraints on transmission, on flexibility, on other aspects. We did not find a way within any reasonable parameters that we tried to break the system. So for example, we increased the cost of transmission by a factor of 3, doubled losses, limited where you could put transmission, and the system still worked. One thing to especially note here is in these blue bars at the bottom, you can see that the baseline had about 800 gigawatts of conventional nuclear, coal, and natural gas energy use. And at 80%, if you look right there on the 80% line, even with 80% of all power coming from renewables, there were still about 400 gigawatts of conventional power. So it was still providing capacity, but the amount of energy it was providing was greatly reduced. So what does it look like hourly? Here's the conventional system, and you can see the summer peak with the really big peaks during the day for these 4 days in midsummer, showing the natural gas combustion turbines kicking in. And then spring off-peak, you have much less variation, mostly a lot of coal sitting there at the bottom and nuclear. And you don't see those combustion turbines because they're idle most of the year. They're mainly pulled out for peaking moments. Here's the renewable system, 80% of all power coming from renewables. And you can see multiple different renewables coming in. And one of the wonderful things about renewables is that they can be complementary. They can be synergistic. So you have more wind at night and solar during the day. They complement each other. However, when you look at the lower right, you can also see some gray. What is that? That's curtailed power. And so what happens is that, if you have a wind turbine or a PV array, there's no fuel cost. It just continues producing electricity. And so some of that power ends up having to just be dumped. Transmission, the system really likes to have additional transmission, and you can see all the transmission lines. One of the things that is done is you have geospatial averaging, statistical averaging across these renewables. And you also have a lot of movement here of wind from the windy Midwest to the load centers in the east. However, when we put on the transmission constraints, very little transmission, the system still worked. And the reason was that you were able to substitute higher priced renewables that were very near to the load center for the somewhat lower cost renewable resources that were a long distance away. So the system would work even under constrained transmission, but the costs were a bit higher. How did the costs look? Well, the square dots here, you see on the vertical axis, the increase in electricity price relative to the baseline by year across the horizontal axis. The square dots show different estimates by EPA, and the lines by EIA back in the 2009 period, 2010 period, when people were looking at energy, carbon markets. The band shows the results of the Renewable Electricity Futures Study The upper end is if efficiency is frozen at 2010 levels. The bottom line is where we're already almost at in terms of the efficiency improvements just in the last 7 years for renewables. And you can see there's only a 3 or 4% difference from the baseline. With where we're going, like the Sunshot 2030 goals I showed, we would actually have a net savings compared to the existing system. 80% reductions in carbon from this. 50% reductions in water use, no longer need to cool thermal power plants. Land use is always raised as an issue. However, if you look at the actual land disrupted from wind and solar PV, it's about the same area as the very bottom line there, golf courses in the United States. Not a huge land demand, relatively speaking. So the capacity credit for variable renewables, you can see that as PV is there during the day, it's taking more and more of the power in midday and pushing the peak, the remaining peak, to later afternoon and early evening. The result is the famous duck curve from California. And the challenge here is the very sharp increase that you see in the neck of the duck in terms of requiring ramping from conventional renewables. And this feature of reduced capacity credit is seen across all of these technologies. And very briefly, for conventional systems, with baseload, load following, and peaking, you have a high demand, and you get a price that you see in the green dotted line going across in a power market auction. What happens when you bring in renewables? Well, renewables don't have any fuel cost, so they come in at essentially zero marginal cost. The result is that they move the demand for the conventional systems down, and now the price is substantially lower. On top of that, they've taken some of the energy production from the, in this case, both the peaking and the load following plants. So there's a double whammy on the conventional system. They've both lost in terms of price, and they've lost in terms of the amount of energy they produce. It happens again, more renewables go on, and you have a further reduction. Now you're pushed into the area where you have to maintain some of the baseload power plant operation to meet minimum generation performance. So that results in having curtailment. You have more renewables than you couldn't put onto the system while still maintaining the min-gen requirements. The end results, we have lots of ways we can integrate variable renewables. I list here a whole series of some of those that we've looked at and found very positive with very substantial benefits in terms of integration. And we've shown at the hourly level that we can reach 80% of all power in the United States coming from renewable electricity. And the question is, how far? We can go a long ways with renewables. We can do it quickly. They can perform well. The costs are coming down. And we're trying to understand now what are the best pathways to get there. There's much to be done, but the potential for renewables is very bright. Thank you.